Welcome again to Let's Talk Advanced Chemistry, Chemistry 2 with Pastor Dan. We're going to do a review over thermochemistry, specifically the concept we looked at last year, specific heat. When we did, we talked about the 5 different types of energy last year that existed. If you need to go back and review that, there are 5 types of energy that exist. The first type is called mechanical motion, energy associated with movement. Second type is thermal energy associated with heat caused by vibration of particles. The more something vibrates, the more heat it has, less of it, the colder it is. Third one is electromagnetic energy associated movement of electrons. So that's going to be light or electricity, one of those two things. Fourth is chemical. Chemical is energy associated with the breaking or forming of bonds. And the last one is nuclear energy associated with the breaking or splitting and combining of atoms. Alrighty, now we're looking at thermal energy. Thermal energy is defined as energy from the heat caused by vibration of particles. We have either heat or temperature. Now people think these are interchangeable, they're not. Heat is an external measure of energy, so how much energy we have on the outside, that's considered heat. Temperature is expressed in the internal measure of energy. Now you think, wait a minute, the weather, they talk about degrees Celsius. A meteorologist sees the system as inside, so it is still consistent. Heat is expressed usually in joules or calories. Temperatures, degrees Celsius, Kelvin in the metric system, which we use degrees Fahrenheit, some of you are more commonly associated with. And then we also have the release of in reaction that would either be exothermic or endothermic. Exothermic is energy released. Endothermic energy is absorbed. Again, I talked to it last year. If you're going out, it's exit, leaving, going in, entering, endothermic. That's the way it works. All right, now, we'll look at the concept of specific heat. Specific heat is the amount of energy needed to raise 1 gram of substance by 1 degree Celsius. We look at the value of enthalpy, the energy released as heat, and there are 2 ways that we can do that. Last year, and we'll do it with this problem, we talked about delta H, change in enthalpy. We are going to move from here and look at Q. Q is just another way of saying enthalpy problems as well. All right, now, so here's our equation for specific heat. Delta H is equal to M times C times delta T, where again, delta H is enthalpy, energy expressed in joules. M is mass is in grams. Specific heat is amount of heat, which is a substance is dependent. It's an intensive property, which means it doesn't matter how much you have, it's always the same value. The units of water, which we're going to use most often, are 4.184 joules per gram degree Celsius. The units are always joules per gram degree Celsius, specific heat. And delta T, delta, I'm always being change in temperature expressed in degrees Celsius, and delta, of course, means change. Alrighty, now, let's do a problem here. Determine the amount of energy needed to cause 55.89 grams of water to go from 21.67 degrees Celsius to 75.90 degrees Celsius. All right, so we need our equation. Delta H is equal to M times C times delta T. Our graphic organizer here. So put our values down. Delta H, M, C, and delta T. Do we know delta H? Well, determine the amount of energy, so that's my question mark. That's what I'm looking for. Mass is in grams again. Look at the problem. Answer there is 55.89 grams. C, well, it does say that it's water, so it's 4.184 joules per gram degree Celsius, because it's always the same. And delta T, well, we have 75.90. We're going to subtract from that 21.67. The difference there is 54.23 degrees Celsius. Is our equation set up to solve for our unknown? It is, so all we do is plug and chug, do our Gauss-synthesis. This Gauss-synthesis. So we have 55.89 grams times 4.184 joules per gram degrees Celsius times 54.23 degrees Celsius. Checking our units. Grams cross out, degrees Celsius cross out. We're left with joules. Do your calculator right there. Get the value up, and we multiply those straight across. We get 12,677.3319 or 12,607.3, but we have to check our sig figs. I have 4 4 and infinite, so least numbers were before, so 12,780 joules would be an answer. Now, some people don't like the zero there, so we can make it kilojoules, moving it 3 places to the left. That way, we're going to end up with 12.768 kilojoules. So either of those would be correct. All right, let's look at another way we can do this. We can also ask for the values. What is the specific heat of a substance? If 45.89 kilojoules of energy is needed to raise 456.78 grams of substance from a negative 8.9 degrees Celsius to 178.80 degrees Celsius. Make sure that you change kilojoules to joules. All right, so our equation again, delta H is equal to M times C times delta T. And our values delta H, M, C, delta T. Go through and see if you can identify them. Delta H. So do that right now. See on your own, pause the video, see if you can find delta H, M, C, delta T on your own first. Okay? All right, here we go. Is 45.89 kilojoules. We want that in joules, so we're going to move it 3 places to the right, move it 3 places to the right to get from kilojoules to joules. We have 45,890 joules. Mass is 456.78 grams. C is what we're looking for. That's our unknown. And then a temperature change, where we're going from 178.80 degrees Celsius to a negative 8.99. No, a negative of a negative, opposites, and of a plus. So we're actually going to add those. We're going to get 187.79 degrees Celsius. Now, is our equation set up solved for unknown? No, it's not. So we put what we want down first. So we put down C. What's on the opposite side from C? Opposite side is a delta H. It still is. So we put delta H on top. Now, what was with C? M and delta T. Since they were with it, those are going to go on the bottom. M and delta T. Now we're going to plug our values in. 45,890 joules. Divide by 456.78 grams and 187.79 degrees Celsius. Nothing crosses out. That's because the units are joules per gram degree Celsius. Take your calculator, plug it in there, 445,890 divided by 456.78 equal, divide by 187.79 equal. Get your answer. Remember your sig figs. Your answer should be 0.5350 joules per gram degree Celsius. Remember, we have 4 sig figs here, 5 sig figs, and 5 sig figs. 4 sig figs. So 4 sig figs is the least number, so that's we can have an answer. 0.5350. Remember that 0 is after a number, after a decimal, showing exactness. It is significant. Alrighty, let's do one more problem. Okay, this time, find the mass of iron needed to raise from 14.6 degrees Celsius to 134.8 degrees Celsius. It requires 34.78 kilojoules of energy. All right, you do need to know the specific heat of iron, and that's it there. Pause the video, try this one on your own, see how we do. Okay, let's check our values just so you know. So that's what we should have, 34.780 joules. M is unknown, and our delta T, the difference there, if we go that, is 120.1 degrees Celsius. Units cross out. Answer then, 628.2 grams. Hopefully not too bad. Take care. God bless. Bye.